Alright guys, so in this video today we're going to be talking about preparing alkynes. So we learned in the past that if you have a strong base that's not bulky and a good nucleophile, like N-, it can do an E2 reaction to a halogen that's secondary. Essentially what happened is that these are the leaving groups, and you have beta hydrogens both here and both here. So what can happen is that you can perform an E2 reaction where you can take an H, and you have to make sure there is two H's here. There's one that's wedged, one that's dashed. You have to take the one that's anti to the one right there for BR. What happens is that you form a double bond. You do one E2 as well. And that's what happens. You first do an E2 where the wedge reacts with the one in the dash and forms a double bond. Remember, elimination reactions form double bonds. But the thing is, we have two equivalents. So what happens is that the second equivalent can actually do a second E2 reaction. And it actually goes again to form what we call a triple bond. Now the thing is, if this was an H, you'd have an H at the end. Okay? If this was an H, you'd have an H at the end. But because it's a CH3 in this case, you have a CH3 at the end. Because both your H's from these positions could be gone, and both the BR's could be gone, they'd be eliminated. Because when you see, this is just a solvent by the way, NH3, nothing to stress about, but two equivalents do form an alkyne. What happens after that is that, this is a totally different question, pardon me, but you have formed an alkyne. And you can use alkyne to do many other reactions, like for example, reduction with the Lindlar's catalyst, right? And also liquid metal reduction, right? Those are two things that you're gonna learn about in further videos, but this is just a preliminary step to other steps in a multi-step problem. Like I said, if this was, in this case, this, then you'd form a terminal alkyne. Now we learned in acid base that terminal alkynes, the protons are actually acidic because the carbon there is sp hybridized, meaning that when it has a negative charge, it's be very close to the nucleus because it's an s orbital. Sp has more s character than p character. So if you had an extra equivalent, let's say this would have to say 3 equivalents then, and the third equivalent would do this reaction down here. Now there's a step 1 and 2, so let's take this one step at a time. This would be N-, take away that to make a C-. Now step 2, you see a methyl and a halogen. We remember our table that methyls and halogens are SN2 reactions when you have a nucleophile that is negatively charged. In fact, if it was a weak base poor nucleophile like water and alcohol, there'd actually be no reaction for both methyl and primary. I digress, but the point being is if I have a methyl substrate and a negatively charged carbon created from step 1, I can go ahead and perform an SN2, and essentially, and pardon me, if I were to use this exact example, this would look like this, because that's what the product looks like here. It has 2 carbons coming off of. I just want to make it very clear for you guys. It will look like this. And you'd add that new methyl group by performing that SN2, because that C- does the backside attack to that methyl, kicks off the I as a leaving group, and you add a new methyl group. So yeah, just to sum it up, that would be the case where you'd be careful. It'd say 3 equivalents in the reactants. But because our initial problem didn't start with an H, there started with C, we ended up with just carbon at the end, right? But in order to go from here all the way to here, well, to here at least, you'd say 3 equivalents. Okay, so that summarizes preparing alkynes, just multiple E2 reactions. So if you see like bromines, 2 bromines on the same carbon, and then hydrogens of neighboring beta hydrogens, and NH-, you're going to be most likely doing a multiple E2 reaction and forming an alkyne.